Hey guys, welcome to another video of Deep Learning Hero. So I'm starting a new video series called AZingML. Basically, we're going to talk about different machine learning concepts which are very important in a fast yet informative manner. And our first video is going to be about an important concept in machine learning called the bias-variance trade-off. So you might have heard when people talking about models, they refer to models as some models have high bias and low variance, and some models have low bias and high variance. And when you are learning these concepts, you might have even seen this particular dartboard example. However, I find this dartboard example very unintuitive because it lacks that machine learning flavor. For example, what do these rings mean? What does the middle mean? And what do all these green dots mean? It doesn't really have that connection to the machine learning problem. So we're going to see the bias-variance trade-off from a machine learning lens. Particularly, we're going to use a regression problem. What is a regression problem? Well, regression is one of the ways you achieve machine learning. Predominantly, most of the machine learning problems you deal with fall into one of these categories: classification or regression. In classification, you are interested in, given an input, which category out of a discrete set of categories that particular input belongs to. For example, take an image classifier. Let's say we have a classifier which is trying to detect cats, and you give an image of a cat, goes through a deep neural network, and it outputs a probability distribution of a discrete set of objects. For example, in our case, it's a cat, a dog, a human, and an alien. And since it is a cat, it gives a high probability to the cat. Next, in regression problems, you are interested in, given an input, predicting a continuous value instead of a output from a discrete set of outputs. For example, in our case, we are interested in developing a property price estimator, and you take features like the number of bedrooms, the area, and in which suburb the property is in. And it goes through a regression model and outputs the property price, which is a continuous value. And I find the regression problems much easier to explain the bias-variance trade-off, so that's what we are going to use. The bias-variance trade-off is better understood if you take a probabilistic view at it. Unlike frequentists, Bayesianists love to run things multiple times. And running things multiple times and having multiple versions of the same thing is one of the essence in the bias-variance trade-off. Basically, there's three things you need to remember. You have different data sets generated by the same underlying distribution. You can think of this as different data sets provided to you by different companies who try to solve the same thing. Then, fitting the same model on each of these data sets separately. Then you have a number of fitted models equal to the number of datasets you have. Finally, you try to predict or see how different models behave given an unseen data point. This data point has not been a part of the original training set you used. And this forms the essence of bias-variance trade-off. Great, now let's solidify our understanding by walking through a scenario. In this scenario, you've been given 5 property datasets by 5 different real estate agents, and they're all interested in predicting the price for a certain property. And they believe that you can predict the property price just by taking the number of bedrooms, and that's what we see here. On the x-axis, you can see the number of bedrooms, and on y-axis, you see the property price. Each of these subplots represent a dataset belonging to one company. And if you superimpose all these data, you will get some graph like this. You can see generally all the data provided by all the companies fall in the same region. However, there's an important thing you need to learn. Data consists of a true signal or a function that we are actually interested in modeling plus some irreducible noise. What does this irreducible noise look like? For example, in our case, there might be a person who bid higher because there was a pool. However, whether there is a pool or not is not part of the features we're interested in, so it looks like noise in our modeling case. And there might be another person who bids lower because it was winter and they were not feeling that great. And there might be another person who thought it's a good price just because his instincts told him so. Like that, there could be different reasons for this irreducible noise. Now, let's go through some modeling options we can use to model this data. Option 1, linear regression. If you fit models on each of these datasets, you will get lines like this. So we have 5 different datasets and we're going to get 5 different lines because of that reason. And each line represented by a certain color corresponds to a company whose dataset is also represented by that same color. And this black dot to the right of the plot represents that unseen property we are interested in predicting for. You can see that all these lines, in terms of the prediction for that unknown property, falls in a very precise region. However, they fall quite far from the actual prediction. Why is that? Because the underlying assumption of the model we used does not comply with the actual dataset. This dataset is not linear. Linear regression expects the data to behave linearly. However, in this case, the data is actually generated by a log function. Therefore, the data is non-linear. And by trying to fit a linear model on a non-linear dataset, although we get very consistent predictions given by all the models, they tend to be wrong. And that leads to a high bias model because all your predictions are very consistent. Due to the problems with the model assumption, it leads to a wrong prediction. Next, if you look at the variance refers to the variance of the predictions given by different models. And you can see that all the predictions produced by this model around that black dot region falls in a very precise area, leading to low variance. Therefore, linear regression is a high bias, low variance model. Next, let's look at the other extreme. Let's fit a polynomial regression model with a degree of 12. What does the degree mean? For example, if you take a second degree polynomial with one feature x, then the polynomial equation for that would look like this. Y equals a1 multiplied by x plus a2 multiplied by x squared plus b. Like that, if you extend it to a degree of 12, you will get a very complex equation. And that's what's happening here. You can see that due to the degree of freedom provided by the degree 12 polynomial function, our models tend to vary quite a lot. However, they have much loose assumptions compared to a linear model and offers a very high degree of freedom, which leads to these varying lines present in the plots. This means that the model doesn't assume much about the dataset and it has enough freedom to wiggle and model the data. This means that our polynomial regression model has a low bias. However, look at what's happening near that black dot. They're saying very different stories. For example, the red line is saying the property's price is very high. However, the orange line is saying the property price is low. This leads to very inconsistent predictions by different models. So the variance around that region is very high. Therefore, the polynomial regression model with a very high degree leads to a low bias, high variance model. Next, let's come to the middle. Let's try a polynomial regression model of degree 2. That will give you a very nice representation of the actual underlying signal. And as you can see, near that black dot, not only the predictions are consistent, but they also fall around the exact region the true property price is in. So this is the best you can do with this dataset. And if you're interested in the code that is used to generate all these graphs, the link will be in the description. Great, now let's summarize what we just learned. In option 1, we had a high bias, low variance model. High bias meant that the model assumptions that the data should be linear led to an inaccurate prediction. Because the linear regression model has less parameters, it varies very little. for different datasets. This concept is also known as underfitting. Next, we have the polynomial regression model with a very high degree. This leads to a low bias, high variance model. It is a low bias model because the model assumptions are very loose, and it leads to giving more degree of freedom to model the data. However, because of having too many parameters to tweak, it has a lot of wiggle room, which leads to a lot of variance, therefore high variance. This is known as overfitting. Finally, the best option we have seen so far is using a model that has a moderate degree. It leads to a low bias, low variance model. Now, I want to bring you to a very important message. I actually have understood the bias variance trade-off in an inaccurate way, and I was fortunate enough for one of my colleagues to spot that, and I was able to correct myself. Whenever I make a mistake, there's something I love to do. That is, trace back my steps and see where I got it wrong. Here's where I got it wrong. I feel like this could be a common trap where people can fall into, so it's good to know the wrong way so you can avoid it. Now, the bias variance trade-off, it's not about a single fit on a single dataset. You can fall into this trap if you are a frequentist. If you think about the bias and variance, there are different biases and variance in a modeling problem. For example, you can think about the model biasing the training data, or in terms of variance, you can think about the unexplained variance in the data when you fit a model, similar to the variance you use computing R-square metric. However, this is not the way to go with the bias variance trade-off. The bias variance trade-off comes from a probabilistic background. It's about fitting multiple models on multiple subsets of data and seeing what happens on an unseen data point. Here are the takeaways. You need to think like a Bayesianist in order to understand the bias variance trade-off correctly. It's about what happens when I got multiple datasets, multiple fits of the model, and I want to see how it behaves for an unseen data point. That's what the bias variance trade-off is about. High bias and low variance leads to underfitting, whereas in low bias and high variance leads to overfitting. Great, that brings me to the conclusion of this video. A quick announcement. I have recently released my new book, which is called TensorFlow in Action. If you're keen to learn about TensorFlow and all its amazing features, I recommend you to check this out. You can find the link in the video description. It teaches you about implementing various state-of-the-art architectures in TensorFlow, creating optimized data pipelines, solving problems like overfitting, and a plethora of applications like image classification, segmentation, sentiment analysis, and etc. and much more. So make sure you check that out too. And if you're interested in getting the code exercises for this video, the link to them will also be in the video description. Thank you for watching this video, guys. I'll come to you guys again with another video.